right, thank you all for coming to my PETS talk on fast privacy preserving punch cards. So the topic of this talk is going to be punch cards. So this is a loyalty program you've probably seen at many stores where you get a card when you go there, and each time you buy something, they give it a hole punch. And once it has enough hole punches, you can redeem the card for some reward. So that's what we're going to be talking about today. And in particular, we're going to be talking about how punch cards can go digital. So there's a lot of advantages to taking your company's loyalty program digital, and this applies for punch cards as well. One great advantage is customer convenience. It's easy for customers to carry around their phones. They're almost certainly already carrying around their phones. So why not use that for the punch card instead of having to have a physical punch card in addition to that? If things are on your phone, there isn't the possibility of losing your card. So you don't have this situation where you have a bunch of different cards, each of which has one hole punch in it. It allows for easier bookkeeping because it makes it easy for computers to kind of keep track of how many people are using your punch card program, how many cards are being redeemed and stuff, instead of requiring employees to kind of count up how many cards are being used. It makes it harder to counterfeit these cards. So for one example of this, I'm using pictures from an eatery I like, and I'm hiding the name, but I saw that they use this kind of custom looking hole punch that has this B shape for each punch. And I went online, and within 10 minutes, I was able to find an identical hole punch on Etsy. So, for the price of one bowl, you could get the punch card, and then you could get a second free bowl by just faking the hole punches. So very easy to counterfeit. Things get harder to counterfeit when it's made digital. And as an added benefit, when it's on your phone, the hole punch process can be contactless, which is not the case in the physical punch cards. So on the other hand, there's one kind of big reason to not go digital. And this is when a loyalty program becomes digital, it has this tendency to become a data stealing monster and collect huge amounts of information about customers by kind of linking together all of their different transactions at a business. And there's kind of an asterisk here because I think for a lot of businesses, maybe that's actually a feature. But for the purposes of this talk, I'm interested imagining a business that cares about the customer's privacy, wants to protect the privacy, but still wants to get all of these other benefits of having a digital loyalty program without having to subject their customers to kind of additional surveillance. So wants to give strong privacy guarantees to customers while still giving the business all of the benefits of having a digital punch card. So the question we want to answer is, can we get the benefits of digital loyalty programs without sacrificing privacy? So there's a lot of tools in the cryptography literature that can help us do this. We could use anonymous credentials, we could use eCash, we could use the Usentive system, and all of these tools, what they do is they give customers an unlinkable token that they can use for each purchase that they make. And then at the end, after receiving several tokens, customers can redeem the tokens by presenting a bunch of them at once. And if you need 10 punch cards, 10 punches to get a free item, you'll present 10 tokens, and then you'll get your free item in exchange for the tokens. The tokens are unlinkable, so it doesn't reveal anything about it. It doesn't allow the business to link together the customer's transactions. This gets the job done, but the work will scale linearly in the number of hole punches, because for each hole punch, you need an extra token. That means extra storage in the size of a token. This means that the server needs to kind of keep track of as much stuff as there are hole punches, not as many things as there are tokens. I mean, not as many things as there are redemptions. So there's kind of a lot of extra work that's linear in the number of hole punches, and that's not great. So there has been a line of work recently, and you can see some of them on the slide. And these works present techniques that can be used to get punch card storage and performance that's independent of the number of punches. So no matter how many punches you need on your punch card, the storage and kind of cost performance is going to be the same. Additionally, these works provide support for broader functionalities. For example, I'll talk about this more in a minute. There's support for what they call offline double spending. There's support for kind of penalizing people and giving them negative points. There's support for partial redemptions, where someone, instead of spending all of their points to redeem something, has like several reward points in their budget and can reward some of them for different kinds of prizes. So this is kind of a nice set of features, and it gets rid of this asymptotic issue. But one partial drawback to these things is that their performance could be improved. Often they rely on pairings or involve zero knowledge proofs. So the performance is not as strong as it could be, and we're going to see if we can improve that. And another issue is I think there's kind of a mismatch between the schemes and the punch card deployment scenario. So this is not to say that these are not useful in certain use cases. And in fact, they provide support for kind of very general loyalty programs, which is great. But what I'm saying is that for the punch card scenario itself, these might be overkill. So one example of this is this feature called offline double spending, which allows detection of if somebody redeems the same punch card at two different locations, but the locations aren't connected to the internet, so they can't kind of check against each other in one live database. There's a mechanism for checking and seeing if offline later if somebody double spent, and then that gets tied back to the person's identity and they can be penalized. Now, I'm saying this might not be great for punch cards because one, oftentimes if you're using a punch card, you're already connected to the internet because the point of sale terminal requires an internet connection. And also in terms of performance, this offline double spending check can be expensive. But perhaps most importantly, when you have this way of checking somebody after the fact and seeing if they double spent, this means that their punch card is somehow tied to a notion of real world identity. And this real world identity is revealed only if somebody tries to cheat, but still there is a real world identity that's connected to this. And this is not something that we need for punch cards. We want it to be kind of minimally privacy invasive. So even if it's protecting your privacy, you shouldn't have to upload sensitive information about yourself in order to use the privacy preserving system. So we want to build something that kind of doesn't have any of that. So in this work, we focus on the requirements for punch cards specifically, and we will not have any long-term user identity tied to public keys for the clients. In fact, clients will not have public keys at all. There will be no server work required to issue cards. This avoids a potential denial of service situation where you kind of accrue a bunch of punch cards with 0 punches on them. And also, we're going to minimize round complexity. We're also going to improve performance. So we're going to remove the reliance on pairings that was present in most but not all of the prior works. We're going to get a 14x faster card punch with 11x less communication to punch a card compared to the best prior work. And we're going to have 128 times faster card redemption and 55x less communication to redeem a card compared to the best prior work. So we have kind of significant improvements by focusing on the punch card use case. In terms of the functionality that you need in a punch card, there's going to be some server set up to initialize server secrets and create a database of redeemed cards to make sure people aren't double spending them. Then we need a mechanism for card issuance so that a customer can get a fresh punch card. There needs to be a mechanism for a card punch so that when someone buys something, they can add a punch to their existing punch card. And there needs to be a way for cards to be redeemed or validated so someone can submit a completed punch card to get a reward. In terms of security, I'm just going to kind of sketch at a high level what we want in terms of security. So we have a privacy requirement that the server shouldn't be able to link any issuances, punches, or redemptions to each other. So you want this to be just like a paper punch card. And the way we define this is by requiring that the server can simulate everything it sees when it's issuing, punching, or redeeming cards. So it doesn't really learn anything from its interactions with customers. There's also a soundness requirement. You can think of this as an anti-counterfeiting requirement. And this is that a client can't redeem more punches than it has received. So here we capture this with a security game where the challenger allows the adversary to punch and redeem cards, and the adversary can kind of play the role of many users. There can be honest and malicious users. Security is adaptive, so it's kind of a good security definition here. And the adversary wins if more punches are redeemed than given. So if the adversary is able to get a certain number of punches, but then redeem more points than it got, then it wins the game. So let's see how we can build a scheme that satisfies these things. And as a first attempt, we're going to have something that actually has no security, but it's just to get us thinking about this. And the idea is going to be that the server is going to take a group element and it's going to raise it to a secret power for each punch. So the server is going to have a secret value in ZQ. It's going to choose randomly. And a client, when it gets issued a punch card, is just going to pick a random group element in a group of order Q. And that's it. There's no interaction. And this is actually a property that we're going to keep all the way through our final scheme. So to get a hole punch, the client is going to send its group element over to the server. The server is going to raise it to its secret, and then it's going to send it back to the client. And then at the end, once the client has n punches, where n is the number of punches it needs for a reward, it sends its original group element and the element that's been raised to the secret key n times to the server. And the server checks that they have the correct relationship. That is that the original group element has in fact been exponentiated n times, and that the original group element had not been redeemed before. So this satisfies kind of a correctness property, but it doesn't have any privacy, nor does it have any soundness. So let's see how we can add those properties in. So to add privacy, the idea is going to be straightforward. The client is going to mask the punch card before sending it to the server. So we have the same protocol as before for a punch, But now, whenever a client wants to get a hole punch, it picks a random element M in ZQ to mask its secret, to mask its punch card. It's going to raise the punch card to the mask, and it's going to send that to the server. Then the server punches that by raising it to the secret key, and then it sends it back to the client, who raises it to the inverse of the mask, which removes the mask and gives the client the group element raised to the secret key. So this way, each time the server sees a punch card, it's really seeing a random group element. So this is great, but it only provides semi-honest security. And the reason is that when it comes redemption time, the server can kind of do an attack where it will distinguish between, it can kind of mark people and distinguish them later. And the idea is that to do this, the server raises one punch card to a different power than it raises the other punch cards. And you can think of this as the digital analog of having one punch card, a hole puncher that you use for everybody. And then if somebody's a bad tipper, you use a different punch card. So then, at the end, when they try to redeem their card, you see, oh, this is the guy who was the bad tipper. You have a different hole punch on yours. So to do this digitally, the server will just kind of raise everybody to the same group element, except to the same secret, except for one time it'll raise somebody to a different secret. And then at the end, when that person wants to redeem their card, the server will see that it's not, this card hasn't been raised to the main secret 10 times or n times. It's been raised to the main secret n-1 times, and it's been raised to this different value one time. So to get around this, we're going to have the server provide proof that it raises a punch card to the same power each time. And to do this, we're going to have the server setup modified so that it also includes a server public key, which is just going to be the generator of the group raised to the secret. And then every time the server does a hole punch, it also sends a Chom-Pedersen proof to the client. And this is just a proof that of two things. One, that the server has a secret, which is the secret that goes into the public key. And second, that the punch card has been raised to that same secret. So this is kind of a proof that these things form a DDH tuple. So it's just each time the server does a punch, it proves that it's doing kind of an honest punch, and the client verifies that. So this gives us a system that actually has privacy. The one thing that we need to now add is soundness, which we currently don't have. And the reason we don't have it is as follows. So right now in the redemption process, the client is sending a group element that it chose as its punch card, as well as that group element raised to the secret n times. And the server kind of checks that relationship holds, and that the original group element hadn't been redeemed before. Now the attack works as follows. A malicious client first behaves honestly, creates a valid punch card, and redeems it. Then the malicious client takes one more punch on the card that had been redeemed. So this takes Pn, which is like the final value of the punch card, and gets it punched one more time. And of course, remember, there's privacy here, so the server doesn't know that it's punching the same card again. Then the client takes the card after it had been punched once, and the card after it had been punched n+1 times, and it submits this as a fresh punch card. Now, the correct relationship is going to hold between these, and the group element raised to the secret once is going to be different from the original group element, so it hasn't been redeemed before, which allows the server to redeem it a second time. So now the client has gotten n+1 punches, but it has redeemed 2 n points, and this breaks our soundness requirement. So the idea for fixing this is that we want to make sure that the client can't redeem a punch card P0 unless it knows the pre-image of a hash function that outputs that value. And what this kind of does is it kind of anchors the beginning of a punch card to the hash function, so you can't take a punch card that's been punched a few times and then use that value as like a fresh punch card. So how this is going to work is we're just going to change the issuance process. So it's still going to be non-interactive on the client, but now the client is going to start by picking a random a lambda bit string and passing that through a hash function modeled as a random oracle. And that's how it's going to pick its group element, instead of just picking a group element randomly from the group. And then at redemption time, instead of sending the initial group element for the punch card, it sends the ID that gets hashed to produce the initial group element. And since the client isn't able to kind of invert the hash function, if you model it as a random oracle, then the client kind of is forced to use only this initial ID and start the punch card at the first punch, not somewhere halfway through, and this rules out the attack from the previous slide. So that's kind of how we build up our whole scheme. There's some extensions in the paper that I'll mention briefly at the end, but that's it. I want to tell you a little bit about our implementation, though. So what we did is we actually implemented all of the crypto in Rust, and then I had a Java Android wrapper around that. And the main construction is implemented using the curve 25519 Dalek library as the elliptic curve. And I evaluated this on a Pixel 1 client for the punch card client, and then a recent ThinkPad laptop with an i5 processor as the server. And I evaluated this both on an empty database of used cards and a database of 1 million used cards to see if it actually made any difference. And it turns out it makes really effectively no difference in performance, because this is just one hash table lookup on the server. So the numbers are kind of comparable. And since in some prior works, having a larger database of previously redeemed cards is much more expensive, all of this evaluation is done assuming there's an empty database of used cards. So there's been no redemptions prior, and we're starting to do redemptions now. And this kind of puts the work we compare to in the best possible light. Here you can see the performance of just of our scheme. And you can see in the red boxes are kind of each step of the process. So there's issuance in the first box. And then the second box is the client and server sides of the hole punching, and then the client and the server sides of redemption. And you can see that in computation time, the client side is always more expensive. And this is because the client is a phone, whereas the server is a computer. And you can see the amount of communication required is really rather small for every part of the protocol. So here we're going to compare to several of the prior works I mentioned earlier in the talk. And the prior work is evaluated on sometimes on different hardware, sometimes slightly worse, sometimes slightly better. So you can take it with a grain of salt. But the main thing to see is that the performance improvements we have are 1 or even 2 orders of magnitude over the other works. So of the prior works, BBW is kind of the fastest in all categories. And then our work gets 1 or 2 orders of magnitude improvement over that. And you can think of this as being like, this is the benefit of focusing specifically on the punch card use case instead of building something general and trying to retrofit it for punch cards in particular. There's also here comparison and communication. Only a couple of works show the communication costs, but you can see here that we're getting a order of magnitude reduction in communication compared to prior work as well. So to wrap up, we're able to get an order of magnitude reduction in card punching time as well as communication, and 1 or 2 orders of magnitude improvement in redemption. And this is, and also having qualitative improvements to better capture the punch card setting. And we're able to do this by 1, focusing on the punch card setting, 2, removing the need for pairings or expensive proofs that are used for kind of more elaborate functionalities. So you can see the paper for more details and extensions. One extension that I think is worth mentioning is we're able to use pairings to actually privately merge partially used punch cards. And this still gets you performance that's better than most of the prior work as well. The code for the project is available online. And if you have any questions, feel free to contact me at saba@cs.stanford.edu. Thanks.